theorems on subspace. Let the first theorem, I'm going to take here color, say, okay, let V be a vector space and W is any non-empty subset of V, then W is subspace of V if and only if it is closed under addition and scalar multiplication. So first we assume here, given W is subset of V and W is subspace of V, and our claim we want to show that W is subspace W is closed under addition and scalar multiplication. Now since W is a subspace, of V, implies W is itself a vector space, and this implies, and therefore W is closed under vector addition and scalar multiplication. By using the closureness property. Using what? Using closureness property of vector space. Of vector space. Conversely, suppose W is closed under vector addition and scalar multiplication. And given and W is subset of V, our claim is W is subspace of V. That is, we want to show that W is itself a vector space. So that is, we want to show that W is vector space. Now the first property, C1, since W is closed under vector addition, implies for any two vector W1 bar and W2 bar belongs to W, their addition is also belongs in set W. Why? We using it is given, since it is closed under vector addition, and C2 is also verified. Why? If K is any scalar and W bar is any vector from W, then KW bar is also belongs to W. It is also what? Given part. Now A1, since W is subset of V, and this implies if W1 bar and W2 bar belongs to W, implies W1 bar and W2 bar belongs to V. So this implies, since V is a vector space, this implies w1 bar plus w2 bar is equal to w2 bar plus w1 bar. Since it is a vector space, means what, it is a commutative. Similarly a2, since for w1 bar, w2 bar and w3 bar in w, and w is a subset of v and v is a vector space, this implies w1 bar plus w2 bar plus w3 bar is same as w1 bar plus w2 bar plus w3 bar. Why? Since v is a vector space. Now next a3 and a3. Now since what is given, it is closed under vector addition and scalar multiplication. So as we know that since I am writing here 0 into u bar is equal to 0 bar, so if we take here take k is equal to 0 and w bar is any vector in w, since it is closed under scalar multiplication, since kw bar belongs to w implies 0 w bar belongs to w. But what is 0 w bar? Using this formula, 0 w bar is what? This implies 0 bar belongs to w, and this implies, and therefore there exists additive identity in w. Now a4, now let w bar be any vector in w, and if k is any scalar, k is equal to, take k is equal to -1 is any scalar. Now we know that since kw bar belongs to w implies -1 into w bar belongs to w. But again, by using previous theorem, in previous lecture theorem, -1 into u bar is equal to -u bar. If you see our my previous video, you can see this property. We have already proved this property. So this implies -w bar belongs to w, and therefore if w bar belongs to w, implies -w bar is also belongs to w, and therefore there exists, this implies there exists additive inverse for every vector. Now m1, let alpha be any scalar and w1 bar and w2 bar any vectors in w, and w is a subset of v, and therefore since v is a vector space, this implies alpha times w1 bar plus w2 bar is equal to alpha w1 bar plus alpha w2 bar. These properties are very trivial. Only important property is what? a3 and a4. So these two properties are very important. I am using this color here. This property a3 and a4 are very important, but remaining property are carry forward because w is a subset of v and v is a vector space. Now m2, now for alpha beta be any scalars and w bar be any vector in w1 bar, you can say here w1 bar, then alpha plus beta, since w is a subset of v and v is a vector space, so alpha plus beta w bar is equal to alpha w bar plus beta w bar. Since what, these properties are very simple, because w is a subset of v and v is itself is what? A vector space m2. Similarly you can verify m3 for alpha beta any scalar and w1 bar be any vector in any vector from set w which is a subset of v and v is a vector space, implies alpha beta w1 bar is equal to alpha times beta w1 bar. And m4, since for 1 into w bar is equal to w bar. Why? Because w bar is what? W bar is equal to belongs to vector W, and which is a subset of V, and V is a vector space, and therefore this implies W satisfy all the 10 axioms. From this we can say that set W is a vector space, and since W is subset of V, this implies W is subspace of V. W is what? Subspace of V. Now next theorem number 2. Let V be a vector space. And W be any non-empty subset of V. V be a vector space and W is any non-empty subset of V, then W is a subspace of V, then W is subspace of V if and only if W is if and only if, say here, Ku or Ku bar plus LV bar belongs to W for any scalar K and L and vector U bar and V bar in W. So we want to prove that if this condition is satisfied, then W is what? Subspace of V. So now suppose we first assume that what is given here, W is non-empty subset of V and W is a subspace of V. Implies W is what? Vector space of V. W is a subspace of V implies W is itself a vector space. Implies Ku bar and Lu bar belongs to W. Okay, by using closureness property. This is what? By using closureness property. That is by using C2, closureness property C2. But again by using closureness property C1, Ku bar plus Lu bar belongs to what? W. For any two vector, their addition is also belongs to W because W is a vector space. By using the closureness property C1. Now conversely, suppose Ku bar and plus LV bar, Ku bar plus LV bar, here not U bar, it is V bar, LV bar belongs to W, and our claim is W is subspace of V. So by using previous theorem, we want to show that it is closed under vector addition and scalar multiplication. So the first if we take here K is equal to 1 and L is equal to 1, then U bar plus V bar belongs to W, and therefore it is closed under vector addition. And if we take here K is equal to 1, if we take here L is equal to 0, then Ku bar belongs to W for any vector U bar, U bar and V bar in W, and any scalar K, and therefore it satisfies both the axiom, and therefore W is subspace of V. Thank you.